I will be discussing an essential component of the marine ecosystem, the marine microbial loop, and its role in carbon cycling. More specifically, I'll cover how incorporating bacterial processes into an offline and online model improves our understanding of dissolved organic carbon and its long-term sequestration in the ocean. So some background on dissolved organic carbon. Dissolved organic carbon plays a crucial role in the ocean's carbon cycle, and it exists in primarily two forms: semi-labial DOC, which has a very short lifetime, and refractory DOC that can persist for a few thousand years. DOC gradients are influenced by oceanic processes such as primary productivity at the surface, creating particulate organic carbon that sinks and dissolves into dissolved organic carbon, which creates this high at the surface, low at depths gradient that we see, as well as mixing processes in the ocean and upwelling in certain regions. Understanding how DOC cycles through the ocean is crucial, as the ocean is one of the largest reservoirs of anthropogenic carbon, and any change to this reservoir could have drastic changes in future warming scenarios. So the study is aimed to develop an offline bacterial model to simulate how bacteria processes particulate organic carbon and contributes to the DOC cycle, and as well as integrating then the microbial loop into the CSM model, testing it against observational data to assess its impact on DOC reservoirs. So the community Earth system model is a global circulation model with atmospheric, oceanic, land, and ice processes, and it includes the Parallel Ocean Program and the Marine Biogeochemistry Library, which simulate ocean carbon and nutrient cycling. This study will incorporate bacterial processes into CSM2 to improve DOC cycling representation. So some key components that are already in the model include phytoplankton and zooplankton processes at the surface, indicated by these purple arrows here. And what I will be integrating are the orange processes of bacterial uptake and mortality and remineralization that change and affect both the DOC-R and DOC-SL pools. And these here are the equations that govern this microbial loop. So when we compare the CSM POC flux to the Martin curve here in the blue line and the black line, which was used in previous studies, we see that the CSM POC flux is slightly different, slightly increased from the Martin curve, but it's still within the bounds of the POC observations from the ocean, which are these dots here. So we will be using the CSM simulated POC flux in the offline and CSM models to see how bacteria respond to this. So from the offline models, we see that our results indicate that incorporating the microbial loop improves the representation of DOC concentration in the model. Some key observations include simulated bacterial biomass being lower than previous estimates, but the model successfully reproduced the observed DOC-R concentration, as seen here in Figure 5. We subtracted bacterially created semi-labial DOC from observations and was able to recreate the estimated DOC-R pool in the ocean. With sensitivity experiments, we looked at the temperature dependence factor and found that using Q10 equals 2, a more representative value of the ocean, slightly increased the production of DOC-SL. And in sensitivity experiments where we increase the temperature by 3 degrees, which is representative of a 3-degree warming at the surface being mixed down through all depths, we see a decrease in the amount of DOC-SL produced, and then we see a decrease in the amount of DOC-SL produced, and then an increase in the production of bacteria per day. So understanding the microbial loop's role in carbon sequestration is vital for predicting how climate change will impact the deep ocean's carbon storage capacity. Future research will explore how changes in DOC-R pools and deep sea circulation affect long-term carbon sequestration. It'll also explore the sensitivity of microbial loop parameters, such as the mortality constant, the yield, and the substrate affinity of bacteria to see if we can match model outputs to observations. And then we will also explore how microbial processes influence the residence time of DOC in the deep ocean. In conclusion, incorporating microbial dynamics into the Earth system models enhances our ability to predict oceanic carbon storage under changing climate conditions. While the study provides important insights, further refinement is necessary to fully capture the complexity of microbial interactions and their role in the carbon cycle. Thank you.